for circuit synthesis. So Sam, take it away when you're ready.
Hello? Excellent. Okay, so hopefully everyone is satisfied after lunch. And at least some people came back, obviously. So now we're going into the hardware segment of the day. I'm going to take it really slow for people that do PL and maybe haven't really touched the kind of hardware that you're actually using. So when you're writing your code, you actually use energy to do that. When you run these instructions and you run your program, like if you type stuff into ChatGPT, you consume so much energy. Like, don't use it just to do silly things. You're like burning so much electricity. And people like me, so I work in the numerical hardware group at Intel, but also doing my PhD at Imperial as well. And we're basically looking at how do we not consume so much power every time we run something through ChatGPT or try and change ChatGPT or whatever it is, right? And this is kind of across the stack. That's why your batteries in your laptops have to get bigger. That's why Apple are really good, don't consume much power. You know, all these interesting things. And kind of, I know we're preaching to the choir here, but obviously EGRAPHS for hardware have actually had quite a lot of interest. I think I've talked to this workshop 3 times about EGRAPHS for hardware, and there's been a bunch of different people also doing the same across the kind of hardware community. So much beyond the PL community, these are all papers and talks at kind of hardware-y conferences. So we're getting out there in these communities as well, which is kind of cool to see. And so the main motivation for most of my work has been all around this. You've kind of got this spectrum. You've got your logic synthesis tools, which are taking languages like Verilog and actually converting them into netlists. And they do these really low-level things like figuring out that a plus should be turned into a bunch of AND gates and OR gates. And they do these kind of clever techniques on gate-level stuff. And then you've got your high-level synthesis tools, which are these clever tools that take C++ and turn those into hardware circuits. And they do things, they always talk about loop optimizations. There'll be lots of talks about loop optimizations coming up, and scheduling and tiling and all these really important things. But you've also kind of got this middle ground, right? So this is actually an exact question I got asked by hardware engineers at Intel the other day. They said, if I take this piece of code, which has just got 2 shifters in it at the top, what are the tools actually doing to this? Are they going and you know, converting it into a different kind of muck structure, so basically a branch, and allowing you to pipe different inputs? And the crucial thing is that now we only have 1 shift, this red shift that you can see down the bottom, and this corresponds to less circuit area, good for power, all these good things, right? You're doing less work to compute the same result. And this is really important, and currently this is not optimized by kind of this end of the spectrum. It's not really optimized by the other end of the spectrum. So we need some stuff in the middle. And that's where this kind of behavioral synthesis idea comes in, which is basically taking kind of word-level hardware designs and trying to do these sort of transformations. That's where really all my work has been focused. And now really we're looking at power optimization, which again really sticks on this right-hand side of this kind of abstraction level. So really we tend to look at fixed data flow graphs, and we're shoving in operators to try and reduce the power consumption. We're just kind of making tweaks after we've basically figured out what design we want to do. But really we can shove this kind of question mark way over to the left, right? We can look at it from a much higher abstraction level and try and apply these optimizations as much more of a kind of, you know, a top element or a kind of primary candidate, not just the power and the not just the performance in the area of our circuit, but can we also take power in at this early design stage as well? And, you know, I actually am no electrical engineer, really. I might be about to get a PhD, hopefully, in electrical engineering, but, you know, all these circuit diagrams don't really mean a lot to me. But the main thing you want to know is this is like a transistor, I believe. And when you basically flip a signal from kind of 0 to 1, so when you're basically having your binary digits going from 0 to 1, every time you do that, you use a bunch of energy, right? And so you can either basically reduce the number of gates, reduce the number of signals you've got passing around, so that means you're doing kind of overall less up and down. So this is kind of this reducing this switching activity, so meaning you're kind of doing less up and downing, and so you're consuming less energy, but obviously you really want to be doing this and producing the same computation. I can produce 0 out of my circuit and use 0 energy at all, and that would be very efficient. And then you can do a load of other things like kind of like operating voltages, so you can have like turbos, like down turboing, I don't know, all this sort of stuff. But this is kind of higher level system design stuff, as well as kind of lower level logic synthesis choices about how do you size your transistors and all these interesting things. So we're really going to be talking about how do we reduce switching activity. So how do we reduce the number of times your signals are kind of flipping up and down between 0 and 1. And I've presented this kind of tool flow about taking some Verilog in at the front end, doing some eGraph rewriting, applying some kind of area and delay optimizations and extraction to pull out an optimized Verilog expression at the end. And what we kind of really looked at in the past is understanding things that in the HLS world, you might view 2 pluses as simply 2 adders, right? But in my ASIC design world, and crucial step is that this is not 2 pluses. This is in fact kind of 1 carry save plus that is by far less expensive than 2 separate adders. And these are like really important optimizations. If you turn these optimizations off in your logic synthesis tools, then you will just blow all of the designs that come out of every big company. They rely on them, and they're super important. And so you've got to maximally exploit those. But now what we're going to talk about is trying to get some kind of new power optimization rewrite. So how do we now apply this and bring that power story? So before, I exactly followed what I talked about, where I said, well, power is just this afterthought, and we'll deal with it later. I was doing area and performance optimization, and now I'm really trying to bring power along for the ride as well. And so how do we actually measure power? Well, we take some circuit representation, be that a netlist, be that RTL, take a workload, mainly I want to render these frames for my graphics application, or I want to, train this neural network with these weights, and run it through your simulator, and you'll basically get, for each of my sort of variables or my signals, I will get some notion of how often are they switching, namely these ones are the really active signals, and these ones are the ones that maybe not so active. And you have 2 kind of notions of power coming out of this. You've got your dynamic power, that's to do with the kind of transitions between zeros and ones that you kind of intended to happen. And you've got this really nasty leakage power thing that we're not going to talk about because that's really hard to model, really difficult, but is also super important and is also a big consumer of like how much are your GPUs actually consuming. And it varies massively depending on the particular hardware design. And so with all that in mind, we've got these new power optimization rewrites that we're going to talk about in a minute. But on top of that, we're going to need to figure out how to do this extraction and how to model power and understand how much power you're consuming with these different choices. And so for that, we're going to have a new eGraph simulation framework. So you can actually simulate a bunch of designs really efficiently. So we'll come on to that, and I think that's probably got a bunch of untapped potential about other applications could really make use of that. So I guess this is the most ridiculous statement that anyone's ever read, but hardware is not software. Clearly true. But why do I think this is important for what I'm talking about today? So basically, when you're executing software, ignore the fact that you can do eager and lazy software. But typically, you're only computing f of x when this A statement is true, right? But of course, in hardware, we don't do that at all. We kind of have these joins at the end, and we'll go and evaluate both f and g irrelevant of what that value of a is, and then we'll just pick from which line we're going to select, right? And so that means that these 2 things are always evaluated. And that's bad, because you're consuming power, because you're doing all those toggling and you're flipping bits to actually evaluate both of these things, but you only care about one of those results. So what a stupid waste of power. Basically, you have redundancy. You've computed a redundant computation. And so all that basically says is that redundancy means you've got wasted power, and that means you've got opportunities to go and save power. And so what we can do is we can say this sort of basic statement, if you take nothing away from this talk at all, I think this is a really useful thing to take away, is that we can basically replace our f with some f prime that really only agrees on this kind of space that we actually care about, namely when a is true. And clearly, this only makes any sense if these 2 things are actually correlated. But we can also say, we've got a bunch of don't care space, basically. And hardware talks a lot about don't care space. We exploit don't care space for absolutely everything. Hardware, performance optimizations, area optimizations. We don't need to handle special cases because someone in the pipeline of our floating point unit has already dealt with the nands and the infinities, so we know we're not going to see them. So we don't have to build a bunch of hardware to actually go and use it. And so really in 2023, I kind of talked about these assumed nodes and how do we understand that, and the work that was talked about an hour ago, something like that, talked about how do we bring context into the eGraph. This was the early attempt at trying to do context in the eGraph. Here we're going to talk about context in a slightly different setting. So what do we actually do when you're going to try and exploit this redundancy? Basically, you've got this ignore most of what's going on, but you've got a bunch of adders going into some muxes where we're going to decide where we're going to take this branch or this branch, depending on a bunch of signals. And crucially, you've got this expensive multiply unit in the middle, this big circle that's kind of redded. And if the buffer signal is 1, then we don't care about the result of that multiplier, and we've just burned a bunch of power for no reason whatsoever. So what we traditionally will do in hardware design is insert these data gating operations where we can basically say we're going to 0 one of the inputs to the multiplier, and that means most of the gates throughout your multiplier circuit are not actually going to go and toggle, and so you're not going to consume any power. Woohoo, you've saved a bunch of power. You didn't do a redundant computation. You just basically produced 0 when you could have produced the actual correct result, but you didn't need it, right? So why would you waste the power? And this is what a lot of power optimization work has talked about. It will say, let's look at these branches, these muxes within your code, and figure out where the redundancy is, and just 0 stuff out and do other things like that, right? So this is basically, we've just inserted an additional operator. But there's a bunch of other redundancy, sources of redundancy, right? If we're going to put registers and we're not going to enable the register, namely we're not going to clock through into memory some of these signals. We can saturate, we can mask, we can shift, and not really relevant as to what these are, but basically you have other opportunities which we should easily be able to exploit in a term rewriting system. Woohoo, EGRAPHS, let's use them. So I'm going to really quickly go over, because we probably don't have a lot of time, and nor do you really care about the actual fundamental techniques. But we can create things like this operation here, where we insert an AND gate that basically just zeros one of your inputs, depending on that select line, when you don't care about it. So all we've done is we've literally zeroed one of the inputs because we don't care about it when the select signal is 0, for example. And you can encode this as a rewriting system. Classic kind of egg rewrites. You can shove these through your graph, which is what this second rewrite is. It's basically just propagating these operators through. And you can obviously combine them to create more complex signals. And of course, you need to take in some considerations. If your select line is toggling super fast, right, then you're switching one of these signals between 0 and the actual data that you cared about really often. And that's really bad, because now you're actually introduced more flipping of the bits. And if you introduce more flipping of the bits, you of course consume more energy, and you've actually done a negative thing. And of course, if your data signals are actually not toggling hardly at all, namely they're pretty static, then there's actually no value in adding these additional operators. You're maybe degraded them. Similarly, we can add these kind of transparent registers. These transparent registers are not very exciting. Basically, what they do is, if you're getting data in every clock cycle, they're just going to freeze the data. So you're just going to keep seeing the same thing every cycle after that when this enable signal is low. And so what happens is that you just basically consume no power. It's basically like you're seeing a constant stream of inputs. There's no more toggling on your input lines. Again, we can put these into our diagram and see some power benefit. And again, we can phrase it as a rewriting system, insert the transparent registers, propagate them through the design, and all sorts of joyous things like that. And you've got a bunch of considerations. The last one, which anyone who has any knowledge about power optimization will be clock gating, and everyone will be asking about clock gating. And it's actually not the easiest problem to phrase as a local rewriting problem. But what we can utilize is this nice little benefit. So remember, in the last slide, we talked about creating these transparent registers. We then talked about propagating these transparent registers through our design. And what happens when a transparent register meets a register? You get a gated register. So this is just clock gating. This is how you can phrase it as a local rewriting problem, and you get the desired result without breaking functional equivalence in anything that you do, circa you're clocking everything on the same clock line, before anyone asked that question that I did get asked the other day. And so that is, you can kind of phrase clock gating as this local rewriting problem, which is great, super useful. Again, problems, deal with that. But to give people a perspective, if you don't really care about hardware optimization, basically if you can do clock gating because it's going to consume very little extra area, very little extra, or hurt your performance very minimally, but you're going to get the best power benefit. And again, transparent latches and data gating have different trade-offs. And this is what EGRAPHS are very useful for, evaluating trade-offs when you don't really know which design is going to be best. So let's go and explore them all and figure out which one's going to be best. And so this talk was about how do we bring this abstraction level up and make it like a first-class citizen power optimization so we can combine it with arithmetic rewrites. So this is a bunch of stuff that I've presented this audience before about how do we do kind of hardware optimizations for area and performance. And this can be things like associativity, exploiting the kind of carry save adders that I showed just at the start of this talk, moving your mux tree structure, moving some operators around, and we can just apply them all together because we're in nice eGraph land. And now we have our power optimizations mixing in with our arithmetic optimizations. And obviously we're going to get some different results, otherwise I wouldn't be talking to you today. And I talked about this at the start, this need to evaluate how do we actually figure out how much power, our eGraph after rewriting represents a whole set of different designs, right? And now we need to determine which design is the one we want to go and implement. And of course, there's an extraction problem, but to evaluate power, we need to have some notion of how often everything is toggling within our design, namely how much flipping of the bits is happening at the different signals in our design. And what's cool about the eGraph approach is that now, because everything in an eGraph is functionally equivalent, we only need to simulate one node per E class, and that gives us kind of these signals or a simulation for basically every design within the eGraph. And so that means that your simulation scales with your E classes and not with the number of nodes, not with the number of representations you've got in your design. And stupid example where your number of E classes goes up by 4x, but your number of designs represented goes up by like 1,000x or something. And so now you've got a very efficient eGraph simulation. Is that useful for something else? I don't know, probably. You can probably use that in a bunch of different contexts to get very efficient, simulation of lots of different things. We use it in all sorts of contexts in hardware for verification and for optimization, analysis, all sorts of things. And then, of course, your extraction goes back to just a cost model. So now we've evaluated how often each of these signals toggling. You can actually go and look at how much each of these different nodes. So, of course, I don't know, for example, x plus x versus 2 times x. Maybe a multiplication node is much more expensive than a plus node to compute the same thing in a hardware circuit. So although you get the same kind of switching activity, namely the number of toggles happening in each E-class, the different nodes within that E-class are going to consume different power to produce that same output. And then let's take a kind of brief example where this moving up the abstraction layer kind of helps out a lot. So in prior work, we've taken this circuit in the bottom left or top left and basically inserted these operators represented by these kind of square boxes over here, which are basically just these transparent latches that freeze the input when you don't care about it. So this is basically just reducing the amount of toggling going through this circuit. And you get some power benefit, but you do pay some area penalty. And then if you take all of these arithmetic and kind of more hardware design principles into account, and you don't just let power be this, let's insert some operators at the end, you get this different design. And this is the thing that came out of our rover tool, and you do get a bigger power benefit for a smaller area penalty. And what's happened is that rover understands that, yes, we've now created what was 2 adders, is now 2 adders, but one of them takes 3 inputs. But this 3-input adder is not a scary thing. It's not 2 adders. We shouldn't be freaked out by this thing. It is perfectly safe. It will not cost you that much extra than the 2-input adder. So it's managed to push this all the way down, and thus you've kind of moved all the signals down such that they're not toggling as much because you take into account all of these select lines kind of affecting your data, and then you can put your data gating on the inputs to all these adders. And this is the idea, is that you get a different result if you actually take power into consideration early on in your design flow. We did it to a bunch of different designs, and you get different levels of power optimization and different levels of area penalty, but useful, and hopefully will continue to be useful as we push it across. These are all still relatively small examples. Clearly the next step for our work is really going to be scale. But I will highlight one interesting problem. This design that I showed you as the prior work, so this is really an open question, is not actually reachable via our design flow at all. And that's because it has notions of resource sharing. So you can think about why resource sharing is a really tricky thing to do in like sort of local equivalence rewriting. Because local equivalence rewriting is all about looking up and down your graph, right? In your kind of local graph. Whereas really for resource sharing, you're looking across a graph, namely this operator over here and this operator over here can be shared because we don't care about them at the same time. But this is not really a local property. This is a much more global property. So this is something we're thinking about. I think it's an interesting challenge, not really obvious how to solve it. And maybe it's not a rewriting problem. Maybe it's just something that eGraph is not super tuned for. If anyone has any ideas or thoughts on that, would love to hear them. And thank you, Alessandro, for reminding me to add this slide. We have jobs for internships. We have 3 or 4 interns every summer. In fact, 2 of them, I think, this year are working on projects on eGraphs and hardware stuff. We'll have applications opening in 2024, Q4, in California and in the UK. Work on all sorts of things like numerics and high-level synthesis. And if you want to talk to anyone, Dr. Cheng, who's in the audience, was a intern with us last year. Only talk to him if he actually had a good time. I think he had a good time. But yeah, come and chat if you wanted to think about, getting into Intel and getting into hardware design. Thank you.
All right, thanks, Sam. We have time for 1 or 2 questions.
Thank you so much for intriguing talk. I wonder if it is aware of PDK or process development kit for your optimizations, and also is it working on structural Verilog rather than behavioral Verilog?
So we try and take behavioral Verilog in the sense that then you haven't guided it to these kind of highly performance optimized designs. So that kind of gives the tool a little bit more freedom to move things around. Whereas if you take really, highly optimized Verilog, then you obviously have to kind of undo certain things and then be able to apply certain transformations. You can still apply these techniques and you'll probably look at more of a model of just adding operators rather than necessarily manipulating the structure if you've already pushed it to something highly optimized. First point, I have not really much experience with PDKs, so I can't comment, sorry, but we can chat perhaps.
Okay, let's thank Sam one more time.